Okay, we're still talking about resistors in parallel, and we're looking at this parallel circuit with three resistors. And in this circuit, electric current comes out of the battery and flows around here and gets to this point and divides. Some goes down this branch, some goes down that branch, and some goes down that branch. And we're comparing the current flow here to two other situations. First, this hydraulic system where water is pumped up to the top and fills up this reservoir here, and then it falls through these holes, and some flows down here turning water wheel number 1, and some flows down here turning wheel number 2, and some down here turning wheel number 3. So just as the electrons divided into three paths in the circuit, the water divides into three paths here. And we're also looking at this building where these people are carried up to the top floor by the elevator, and then there are three paths down to the bottom. Some go down the stairs, some go down the ladder, and some go down the pole. Now what I'm going to do is look at the hydraulic system and the building here and explain a concept, an important concept, and then go back and apply that concept to the circuit. Okay, first look at the hydraulic system here. Water falling from the upper reservoir to the lower reservoir loses potential energy. So imagine one particular gallon of water. Just imagine a chunk of water here. It's going to lose the same amount of potential energy regardless of which water wheel it goes through. And you could think of one little gallon or one little cup or one little atom of water. Whether it goes down this wheel or this one, it doesn't matter. The potential energy only depends on the height. If it starts up here at this level and ends up down there at that level, it's lost a certain amount of potential energy. And it's the same amount regardless of which wheel that it goes through. And that's a key point. We're talking about the potential energy, which depends on the height, and it's the same for all three water wheels. The potential energy for each little piece of water is the same for all three of them. Now look at the building. Let's pretend like all of these people are the exact same size, just like all the electrons in a circuit are the exact same size. A person going down the stairs is going to lose some potential energy, and a person going down the ladder will lose the same amount of potential energy, or if he goes down the pole, he'll lose the same amount of potential energy. The potential energy per person is the same for all three of those paths. As long as they're going from this height to that height, it doesn't matter how they get there. The change in potential energy only depends on the height. Now in the electric circuit, the battery provides the electrons with potential energy. That's electrical potential energy. And that energy is lost when the electrons go through a resistor. That energy is turned into heat in the resistor. Now these could be other things. They could be light bulbs, in which case the energy is turned into light, or it could be a motor, in which case the energy is turned into kinetic energy. But the point is, when the electrons come out of the battery, they have some potential energy. So when they're up here along this section of the circuit, they have potential energy. And then as they go through these resistors, they lose potential energy. And that's electrical potential energy. Now when they get down here to the bottom side, that potential energy is gone. And it doesn't matter which resistor they go through. They're going to lose the same potential energy when they go through resistor 1 as they will going through resistor 2 or through resistor 3. And just as we can speak of the potential energy lost by each gallon or each atom of water as it falls through this height, or we can speak of the potential energy lost per person as they come down these paths, we can speak of the potential energy, the electrical potential energy lost by each coulomb of charge. And that potential energy per charge, that's what we call voltage. You might recall our equation for voltage. Voltage is energy divided by charge, and that's energy in joules per coulomb. So imagine electric charge here, and each coulomb of charge is going to lose some energy when it goes down one of these paths. And regardless of which path it goes through, it loses the same potential energy. And since energy is related to voltage, we sometimes call it a voltage drop. If you talk about the voltage drop in resistor 1, you're just talking about the voltage, the energy per charge lost as electrons move through resistor 1. And that's what we would commonly call V1, the voltage for resistor 1. The term voltage drop is often used because as the electrons go around the circuit, there's a drop in their potential energy. Now this concept can be summed up in this statement. For resistors in parallel, the voltages are the same. And we can write it like this. V1 is going to equal V2, and that's going to equal V3, and those are all going to be equal to V, the voltage provided by the battery. So if we look back at the original circuit, this voltage here, V, is the voltage of the battery. V1 would be the voltage drop in resistor 1, and V2 in resistor 2, and V3 in resistor 3, and all of those are the same in this case. For resistors in parallel, the voltages are all the same. Now again, that's a fact that you can memorize, but you'll be far better off if you understand that fact. Now we're going to do a little derivation. And this is a derivation for the resistance of resistors in parallel. And we're going to start with this fact. We're going to start with the fact that in parallel, the current is equal to the sum of all the individual currents. So the total current coming out of the battery is equal to the current in each of the individual branches. And in this case, we have 3 branches. Now remember Ohm's law. Ohm's law says that V equals IR. And that can be arranged like this. I is V over R. So I'm going to take this I and just replace it with V over R. And then I'll do the same thing for I1. But instead of applying Ohm's law to the circuit as a whole, I can apply Ohm's law just to that resistor. And I can say I1 is V1 over R1. And I2 will be V2 over R2. And I3 will be V3 over R3. And then remember that in parallel, the voltages are all the same. So this V1 and this V2 and this V3, that's the same number. And I could factor that out and cancel it out with the V over here on the left. So those all cancel out mathematically. And I'm left with this. 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. And that's the end of the derivation. This is a formula for the total resistance of resistors in parallel. Now it's not actually solved for R, it's solved for 1 over R, but that's commonly how it's written. Just take a look at that formula real quick. 1 over R equals 1 over R1 plus 1 over R2 plus 1 over R3. And some people ask, couldn't we just flip each side? Couldn't we just take the reciprocal of each side and flip the 1 over R over and flip the 1 over R1 over and the 1 over R2 and the 1 over R3? Going from here to here would be a mathematical mistake. We can't do that. What happens if we take the reciprocal of each side, the left side would become R over 1, or just R, and then we would have to take the reciprocal of the right side. Remember, the main idea in algebra is that you can pretty much do whatever you want to do to an equation as long as you do exactly the same thing to each side. So here I've taken the reciprocal of the left side, and now I have to take the reciprocal of the right side, and that would give me this, 1 over R1 plus 1 over R2 plus 1 over R3. And that mathematically is not the same thing as I had on this row. Now this is a formula for R. It's solved for R, but it's not commonly written that way. It's just a little easier to write and to remember written this way. And so that's commonly how we write the formula for the total resistance of multiple resistors connected in parallel. Now, we'll come and do some examples with this in the next video. But just for now, remember that this could apply to not just 3 resistors, but if we had 2 resistors in parallel, the equation would look like this. Or if we had 4 or more, the same concept would apply. We would just add more resistors out here on our equation, as many as we needed. This equation can be a little bit tricky to use, so I'll show you some examples and show you the common mistakes that are often made so that you can avoid them when you need to do calculations of this nature.